Welcome to The Explainer. Today, we're diving into a topic that's really at the very heart of modern artificial intelligence. It's the incredible technology that powers everything from AIs that can beat world champions at complex games to the chatbots that so many of us are using every single day.
I mean, think about that for a second. It's a pretty wild question, isn't it? It almost sounds like magic, but it's not magic. The answer is this really powerful idea called reinforcement learning. So let's jump right in and see how this actually works. Okay, so forget about the usual way you think about machine learning, like feeding a computer millions of pictures of cats. Reinforcement learning is all about learning by doing. You have an agent, it tries something, it gets some kind of feedback, a reward or a penalty, and then it uses that feedback to adjust its strategy. It's basically just trial and error, but, on a massive digital scale. Right. So before any agent can learn to play a game, it needs to understand the game board and the rulebook. And in reinforcement learning, we have a very formal, structured way to define this playground.
This is really just a fancy way of saying that the machine is learning how to make a whole series of smart choices over time. You see, it's not just about finding one single best move. It's about stringing together the entire sequence of moves that leads you to the ultimate prize, like getting a checkmate in chess.
So this is where we get just a little more technical. The official name for this framework is a Markov decision process, or MDP for short. The best way to think about it is as the official rulebook for the agent's entire world. It lays out every possible situation, every choice it could make, and what the consequences of those choices are. It's the blueprint for the whole problem. In this slide here breaks that blueprint down. So first you've got states. That's just where the agent is right now, like a specific arrangement of pieces on a chessboard. Then you have actions. Pretty straightforward. Those are the moves it can make. The transition part? That's just the physics of the world. The rules saying if you do this, you'll probably end up here. Then, and this is key, you get a reward. Points for a good move, maybe a penalty for a bad one. And finally, that discount factor. That's just a little knob you can turn to tell the agent to prioritize getting rewards now versus getting them way off in the future. Put those 5 things together and you've defined the entire game. Okay, so we've got our rulebook, the MDP. Great. But how does an agent actually use that to figure out the absolute best strategy to win? Well, this is where the agent's secret weapon comes in, the value function. Seriously, think of it like a cheat sheet for the game. For any position it finds itself in, it can look at this cheat sheet and see a score for every possible move. And that score basically tells it, hey, how good is this move for winning the game in the long run? The agent's whole job, then, is to figure out what those scores are. Now, this slide shows a couple of the classic old-school ways to solve that puzzle. These algorithms, policy iteration and value iteration, can find the absolute perfect strategy, but they have one huge catch. They have to know all the rules of the game from the very beginning. Still, they're super important because they're the foundation that all the modern methods are built on. And that is where things get really, really interesting. Because, in the real world, you almost never know all the rules up front. A robot doesn't know the exact friction of the floor before it takes its first step, right? It has to learn as it goes. So this brings us to this really big split in how you can approach the problem. Does the agent try to build a sort of mental map of the world first and then plan using that map? That's model-based learning. Or does it just skip building a map and learn directly from trial and error? That's model-free. And, most of the big headline-grabbing breakthroughs you hear about, like AIs totally crushing video games, they're almost all model-free. Why? Because building a perfect map of a complex world is just way too hard. All right, so let's dive into the algorithms that can actually handle the messy, uncertain world we all live in. Q-learning and SARSA. These are 2 of the heavy hitters in the model-free world. And you can almost think of them as having different personalities. Q-learning is the total optimist. It learns by always assuming it's going to make the absolute best move next. SARSA, on the other hand, is more of a realist. It learns based on the actions it actually takes, including all its clumsy exploratory mistakes. And that makes SARSA a bit more cautious, which can be a really good thing if you're, say, a robot learning to walk near a cliff. This brings us to this massive, fundamental challenge, not just in reinforcement learning, but kind of in life, right? It's this constant tug of war. Do you stick with what you know works? Go to your favorite restaurant that's always good? That's exploitation. Or do you risk it and try that new place down the street that might be incredible or might be terrible? That's exploration. Every single learning agent has to constantly figure out how to balance these 2 things. So how do they do it? Well, a super common strategy is called epsilon greedy. It's simple. Most of the time, the agent picks the move it thinks is best. But every once in a while, with a tiny probability, that's the epsilon, it just picks a totally random action, just to see what happens. There are more sophisticated ways too, like choosing to explore actions you're less certain about, or using clever probability tricks to balance the choice. But the goal is always the same. Explore enough to find great new strategies, but not so much that you're just flailing around.
Okay, so everything we've talked about so far works fantastic for, simple problems. But what about something like an old Atari game? Think about it. The state is every possible combination of pixels on the screen. That's not thousands of states, it's billions, even trillions of them. You could never build a table big enough to store a score for every single one. The classic methods just completely fall apart.
And this is where the deep in deep reinforcement learning finally comes into the picture. Since you can't build that giant table, you do something much smarter. You train a deep neural network to estimate it. You just feed the network the pixels from the screen, and it learns to spit out a score, a Q value, for each possible action. And that was the absolute game changer. That's what let AI start playing those games at a superhuman level.
But, it wasn't that simple at first. The learning process was super unstable, it just didn't work reliably. The solution, and this was brilliant, came from two key tricks. First, experience replay. Instead of learning from just the very last thing it did, the agent stores its experiences in a big memory buffer and then learns from random samples of its past. Second, they used a target network. This is basically a slightly older, slow-moving copy of the main network that provides a stable goal to learn towards. Honestly, without these two ideas, DeepRL as we know it probably wouldn't exist.
Okay, so this is obviously super cool for playing games, but it's not just about games anymore. This tech has broken out of the lab and is starting to shape our world in some really significant ways. You might be wondering where, and the answer is, well, pretty much everywhere. And maybe the single biggest, most impactful place you're seeing it right now is inside the AI chatbots we all use. I mean, the reason models like ChatGPT can have these incredibly helpful and nuanced conversations, yeah, that's thanks to a very specific, very clever type of reinforcement learning. It's called reinforcement learning from human feedback, or RLHF for short. And the core idea here is just brilliant. Instead of trying to write some complex code to tell the AI what a good answer is, we just show it. We become the teachers. We provide the feedback, and the AI learns directly from our preferences.
So here's the three-step recipe. First, you start by fine-tuning a base AI model on a bunch of high-quality examples written by humans. Step 2, you have humans look at different AI-generated responses and rank them from best to worst. Then you train a separate model, a reward model, whose only job is to learn to predict what kind of answers humans will like. And for the final step, you use that reward model as the new rulebook. The main AI uses an RL algorithm to practice generating text, trying to get a high score from that reward model. It's this powerful feedback loop that teaches the AI to be helpful and aligned with what we actually want.
And believe me, it doesn't stop with chatbots. This stuff is everywhere. It's used to train robots in super realistic simulations so they can learn skills before ever entering the real world. It's the brains behind world-beating systems like AlphaGo. It's even working behind the scenes, tuning the recommendation engines that decide what movie you see next, learning from what you click on in real time. Heck, it's even being used to optimize traffic light patterns in cities to cut down on traffic jams. It is quietly making all the systems around us just a little bit smarter.
And all this brings us to a really big final question. As we use our own feedback to make AI more and more capable, what values are we actually teaching it? If these systems are learning directly from us, from our collective preferences and biases, then it becomes absolutely crucial to think about the kind of teachers we're being. And that's what makes this whole field so incredibly important to understand.